Hello everybody, in this lecture we're going to discuss multi-layer perceptrons and the backpropagation algorithm. So previously we discussed Rosenblatt and LMS perceptrons which are linearly separable. With multi-layer perceptron we're going to tackle the issue of non-linear separable data. So what do we mean by non-linearly separable? If we take the example of data like this, we have, let's say, this two data. Okay, let's say we have another one here, and another one here, and another one here. So here, we cannot draw a line between those two. What we can actually do is we need some nonlinear function to separate those data altogether. So these cannot be separated by a line, because if you draw any line, it will hit one of these two categories. So now, to overcome this limitation, the multilayer perceptron, or for short MLP, has some characteristics. It has non-linear activation function, and the network consists of one or more hidden layers. So we don't just have input layer and output layer, we actually have a hidden layer, and it has high degree of connectivity. Now, if I want to draw a simple diagram, so let's say we have inputs like this. So this is the input layer. Okay, we present the input here, and then we may have, this is one of the hidden layers. Okay, we have another hidden layer, so this is hidden layer 1, this is this one, this is hidden layer 2, and we can have some output layer. The connectivity is between those is when you have a fully connected network, not necessarily always, but usually it's fully connected. Each input is fed to each neuron in the hidden layer, and by each turn this will be also connected to all neurons in the second hidden layer, and of course this will be connected to the output layer. The second neuron will have the same thing. We will have a connection like this, and of course it has the same connection here, and then here this guy has a connection like this, and we continue for all layers here. If I want to draw the third one here, we can go like this. Okay, of course we don't have a third hidden neuron here, so we don't have to connect that to the output. So all inputs, also this is gonna go like this, and for all of them. So each input input layer is connected to all the neurons in the hidden layer. In turn, each hidden layer to the second, and as many hidden layers as we have, and further to the output layer. So this is a fully connected network. Okay, so now we have two types of functionalities. So if we go ahead and check our two types of propagation, so we're gonna call data going from one layer to the other a signal. So two types two types of signals. Okay, if you look at this, this will be signals, functional signals going like this, going from the hidden layer 1 to 2 to the output, and error signals going back. So we have functional signals, these come from input to the hidden to output layer, and we have the error signals. These are, they originate from output to hidden layers. If I'm gonna draw something like this, I have, so let's say this is a hidden layer. So these are the functional, these are the functional signals, and we have error here going like this, and we have here error signals. So these are the error signals. So now, what are the functionalities of a hidden layer? So the hidden layer actually acts as a feature enhancer. So we have here many inputs. We go, when we have multiple layers, we're going to higher dimensions. So depending on the number of hidden neurons, the functionality of the hidden layer differentiates. So let's say I have 3 inputs, so consider this network. There we go, network. So we have, let's say, 2 inputs and 4 hidden layers and 1 output. So of course, each one will be connected, each input will be connected to all the hidden neurons, and these by in turn be connected to the output layer. So here, this is the hidden layer. Here what we are doing is having features enhanced, since we're going from 2D to 4D. Okay. Another feature of hidden layer can be in compression. So we can compress the data. So if we have like many outputs, and then we have many inputs, and then we have 3 hidden neurons. So here we see we're going to and so forth. And here we are going to here we're going from 5D to 3D data, and here we're doing is compressing the data here. So hidden layers have the functionality of enhancing some features. Maybe some features are not found in the original data set. It takes it to a different dimension where separability is much easier. Or it can go with compressing the data, and this will save some storage. Of course, these hidden layers, they function for, they have computational functions with weights. Okay. Each weight is attached to a neuron, and also it has computation for gradients which will be used in the when we discuss the backpropagation algorithm. So given this fact about hidden neurons, now we're going to start with how can we train this network. So we have two types of training. We have the batch learning versus online learning. So with batch, as the name suggests, we deliver all the inputs at a time. Where online learning, each input is presented iteratively. So here we have iterative method for presenting input and updating weights. And here we have present all data set and then update the weights. Okay, so before going into the differences between batch learning and online learning, let us consider what are the data sets and the error signals. So consider a function, okay, which has x of n as the input, d of n, of course here we're talking about supervised learning, where n goes to 1, capital N. Here n is the dimension of the input. (2D or 3D or 4D), so depending on the number of actually rows. So x of n is equal x of 1 to x of n. Of course, the error signal is presented as follows: E j of n is equal d j of n minus y j of n. So here what we have is j is a specific neuron. So the error of ej of n is equal dj of n minus y j of n. Now the instantaneous error is presented as follows. We have big E of j of n is equal, of course we add the half just for ease of calculation when we're doing the derivative, and this is the instantaneous error, of course all specific to a neuron j. The total instantaneous error is the summation of all errors, of all neurons, for j belongs to C, where C includes all neurons in the output layer. So if we have 3 neurons in the output layer, each one will have an error, ej of n, where j goes from 1 to 3, and then we calculate the error and we sum them over all these output layer. So first we are discovering, we have the input, we have a target value, a desired value. We calculate the error signal for a specific input and specific output for a specific neuron, and then the instantaneous error, which is the half of the square of the error signal, and the summation for all of them. Now this of course will be equal to summation j equal belongs to C for E j squared of n, and here we have the half. Okay,
So this is where G belongs. Okay, so now, given that we have this error signal, we're gonna discuss how batch learning and online learning differentiates. So as we said, for batch learning, we don't do this iteratively. We calculate the average error over the training sample. Since we're presenting the whole inputs before actually calculating and updating the weights, so we need the average error. So E average for the whole training set is equal 1 over n, since we're going to divide them over all, summation n equal 1 to big N, the instantaneous error, which is b equal 1 over 2n, summation n equal 1 over all training samples for all output neurons. So this will be all output neurons, and this will be all training set. So this is the average error for batch learning. We calculate it for all, and this constitutes the cost function when dealing with the gradient. Furthermore, we can see that both the average error and the instantaneous error depend on W. So later on we're going to take the derivative with respect to W so we can minimize the error. Furthermore, in batch learning, each epoch, as we said, in each epoch we present all the training sample, and we update the weight based on minimizing the average error. We shuffle the training sample for the next epoch. This is very useful in parallelization. However, it requires high storage. So this is the advantage and this is the disadvantage. So why do we use batch learning? It's very good for hardware implementation since it's parallelizable, and however it has a high storage demand. Of course, it can be faster since we're not updating every training sample, but we present the whole thing and then we calculate the average error, and we come up with an update for the weights. Now, if we switch gears to the online learning, which we're going to discuss thoroughly in this lecture, we're going to discuss online learning. So it deals with the instantaneous error E of n. Okay, each epoch we consider n training samples and weight updates done after each sample is presented. So if we present a sample and then we update the weight, okay, this goes against parallelism, Okay, however it has low storage. Okay, so of course, as we said, the online training is stochastic in nature. It's less likely to stuck in a local minima, requires less storage. Training data is redundant, so if the training data is redundant, here we can eliminate this redundancy and we present one example at a time. It tracks small changes and simple to implement. So now let's go ahead and discuss the backpropagation algorithm using the online method. So now we're going to start with the backpropagation algorithm, which we're going to discuss now. To draw the schematics of a single, let's say, output neuron connected to a hidden layer or any of the output layers. So it doesn't matter where we are in the network. Well, it matters when we calculate the gradient, but the basic functionality is the same. So let's say we have a bias here. Let's say this is y of 0 of n equal plus 1. So this is one of the hidden neurons, and then we have y of 1 of n, then we go y I of n, all the way to y m of n. Let's say we're discussing here neuron J. So of course this is neuron J. Okay, each input from the hidden layer is connected to neuron J. So this will be W J0. So this is neuron V J of n at iteration n. So this is weight J0. So of course we take the first index from the layer, from the next layer, and the second index from the initial layer. So this is the initial layer, this is the second layer, or the second layer. So Wj of 0. So this will be, of course, Wj of 1. This is Wji, and this is Wjm. Okay, so Vj, this will be applied for an activation function, and then we get Yj of n, which is the output. It's fed into a error signal to get E of Aj of n. So this is the J of n, the desired value. This is the output value, and we get the error Ej of n. So this is the schematic of a neuron J. We have input from the layer before it. We calculate Vj of n. We apply the activation function. We have the computed output. We subtract the desired value, and we get the error signal. Now, if you want to discuss what is Vj of n, so let's start from here and start computing. So Vj of n is, as with the previous models, is summation from I equal 0 to m. So we start from the bias and we go all the way to m. Wji of iteration n, and then we have yi of n. So for each input, we multiply it with its corresponding weight, and we do the added sum. Okay, so then Yj of n is equal the activation function, which can be sigmoidal or any of the activation functions that you want to use, and this is the computed output. So now we have the computed output, and we have the induced field computation. Now let's say we want to minimize the error between those two. So as we did with the LMS algorithm, we need to take the derivative of the instantaneous error with respect to the weight. So minimizing error happens as follows. We need to take the derivative of the instantaneous error with respect to the weight. So as we see, the instantaneous error is a complicated function, and we need to compute this using chain rule. So if we double check, if we remind ourselves what is the instantaneous error, it's as follows. We have Ej of n is equal half Ej square of n, and remember that Ej of n is equal dj of n minus the computed output. We have Vj of n is equal summation of Wji of n times Yi of n, and Yj of n is equal the derivative of the induced field. So now when we want to compute the derivative of Ej of n with respect to the weights using chain rule, so this will be the derivative of the instantaneous error. Okay, the half goes, this is why we add the half, over the instantaneous derivative with respect to the error signal times the derivative with respect to the error signal. Then it depends. D does not any is a constant, so we take it off. So it's be the derivative of Yj of n, and then Yj of n depends on V of n. So Yj of n depends on V of n. So this will be with respect to Ej of n. And then the last one, the induced field depends on the weight. So now what we need to do is figure out what does each of these values constitute. So if we take the derivative of this the first element, this will be the derivative of this will be Ej of n. If we take the derivative of Ej of n with respect to Yj of n, this will be minus 1, because if we take the derivative here, this will be minus 1, this will be constant, this will go. And then if we take the derivative with respect to Vj of n, then this is actually Yj with respect to Vj, it's actually the activation function prime. So there is a j here. Okay, and if we take the derivative of this guy, summation will be left out, and this will be 1. So we are left with yi of n. So in this case, we can write the error of, when we take the partial derivative with respect to of the instantaneous error with respect to Wji of n, it will be equal Ej of n times minus times the derivative of the activation function for the induced field, and then we have here we're missing a parenthesis, okay, times yi of n. Okay, so this is the gradient. So now when we want to update the weights, we have the rule. So the difference or the update of n is equal minus the learning rate, the derivative of the instantaneous error with respect to wji of n. So we add the minus because we want to minimize, okay, and this is the learning rate, this is the step, and this is the value that we need to compute. So now we can write our update equation. So this means wji of n plus 1 is equal wji of n, and then minus the learning rate times the derivative with respect to wji of n, and this will be equal wji of n. So we know that this will be equal to minus ej of n times phi prime j of v of n, bj of n, times yi of n. For simplicity, let's call this the local gradient delta j of n, just for simplicity. So this will be wji of n, the minus will go away, the learning parameter times ej of n times yi of n. So this is the weight update equation. Of course, we have to compute the output, we have to compute the error with the derivative of the activation function with respect to the local induced field, and this is what ej of n is, where delta j of n is the local gradient at neuron j, which is equal to ej of n times phi prime bj of n. Now this is the case for output neurons. Okay. Now the second case is when we have a hidden neuron. What shall we do? So for the case of a hidden neuron, so remember we started from the output, so if I want to go over the last two pages, so first what I did is I started from I calculated the output. Once I have the output, I went back with the error signals and started calculating the gradient. Now what I need to do, what if I have a previous layer here? So if we want to draw it nicely, so if we take the case of the hidden layer, with the hidden layer we have two layers, we have the output and the hidden. So let's say the output is neuron K, let's put it like this, output is neuron K, and this is like the previous case, and the hidden layer is neuron J. So neuron J takes input from the bias, of course, and then we have, this is the first one, and then we have y1 of n, we have yi of n, all the way to ym of n. Of course, this is neuron J. Okay, so these are the connections. they have weights of course, and then here we have Vj of n, and we apply the activation function to get y j of n. Okay, all right, now this will be connected to one of the neurons in the output layer. Let's call it, this is neuron K, output layer. So of course there can be many output neurons. This neuron will be the hidden neuron y of j will be connected to all of them, but we're going to take a single case where it's connected to Vk of n. Of course we apply the activation function, and here we have yk of n, apply -1 with respect to the desired value at n, and then we get the error signal ek of n. So here we notice that we have the hidden layer neuron j, and we have the output neuron k. So now for the hidden layer we need to calculate the local gradient. Now we need to compute the local gradient for the hidden layer. As I said before, we have here the input layer, we have a single hidden neuron v of j, which we compute its intermediate output y of j, and then we have another output neuron v of k. We know how to compute the local gradient for the output neuron, since we have the error signal here. But what about the local gradient? So we have discussed that the local gradient is actually the derivative of, of course, at iteration n is equal the instantaneous error over the derivative with respect to, and we take out of course the wji, since the gradient is only part of the optimization that we're doing when we are computing the weights. So it's if we take a look at it in the previous computations, we see that the local gradient is only part of it, which is the error and the derivative of the activation function. So in this case, what we do is we know that the error depends on yj of n, and y of j of n of course depends on vj of n. So by chain rule we can go from here to here. We know this to be phi j prime of vj of n. However, we need a way to compute the error, the partial derivative of the error with respect to yj of n. So if we start from the output layer, so starting here, starting from output neurons, okay, so we know that E of n is equal half, where k belongs to c, all the output neurons, for e k squared of n. So if we take a look, we have here multiple neurons at the output layer, each of them with a different error. So now we sum them all, and these are, since this neuron v of since the neuron yj of n is connected to all these neurons at the output layer, so we need to propagate the error from all the output neurons to the hidden layer. So the way we do this is we have the instantaneous error for all output neurons. So if we take the derivative of this with this fact, so we can go do like as follows. With respect to yj of n, then we have, this will be the summation. We take the summation out, ek, this is squared, times of n times ek of n over the derivative yj of n. Okay, and this will be equal to summation for k belonging to C, of course, for ek of n, and we take the partial derivative here. Of course, here we have a missing del. So the error at the output layer depends on the induced field at the local at the output layer times the derivative at the derivative at the induced field with respect to yj of n. Okay, so starting with this formula, we can go as follows. Okay, so what we can do is, I'm gonna copy this formula. So we have the instantaneous error with respect to yj of n is equal to the summation for all k times over the induced field. So I'm just copying the formula again with respect to yj of n. Now, so let's take each parameter by itself. So this is the output layer, remember. So we know that ek of n is equal dk of n minus yk of n. So this means it's equal to dk of n minus, this is of course phi k of vk of n, where k is the output neuron. So when we take the derivative with respect to vk of n, this will be equal to, this will be the constant, minus phi prime vk of n. Okay, now we have this figured out. Now we need to figure out the derivative of the induced field with respect to the output neuron. So we know that vk of n is equal summation for I equals 0 to all the inputs we have, wkj of n times yj of n. So now if we take the derivative with respect to vk of n over yj of n, this will be equal to wkj of n, because we are doing the derivative with respect to this parameter. So this means we have, n over yj of n is equal minus summation k of ek of n times phi prime of vk of n times wkj of n. Okay, and we know that this is the induced field at the output layer. So we can do as follows: minus k phi delta k of n times wkj of n. So now we have the local gradient for the hidden layer, which is equal phi prime j of v j of n times the summation of k delta k of n wkj of n, where j is the hidden neuron. Now, if I want to describe it better, if we have, let's say we have, these are the output neurons. Okay, so we have delta 1, delta 2, all the way, oh, this is delta k, delta m. Okay, so each one have error 1, error k, and this is error m. So this is at the output layer, and these all will propagate backwards to hidden neuron j. This is hidden neuron j. Okay, and this is w1j, this is wkj, and this is wmj. Okay, and this will generate the local gradient. Okay, so now if I want to write the update equation for w, so w ji of n plus 1 is equal to w ji of n, and in this case I want to write, I will have the learning parameter times the local gradient times yi of n, and this will be the update equation. So here let's take the case of a multi-layer perceptron where we have two layers. We see L equal to, which is the number of layers, so we have two layers. This is the input layer, M0, this is M0, and this is M1, and this is M2. So here we have the output layer, this is the output, this is the hidden, and this is the number of inputs. So we see that M0 we have 3 inputs and we add a bias. For the hidden layer also we have 3 neurons and we add a bias, and these are the output neurons. So how will the algorithm work in the presence of multilayer? We see that here the weight is W10, which is the bias, B of 1. We put as a subscript 1 to indicate that this is going to the first hidden layer. You see here W13, which indicates that this is the weight coming from the output from layer. Actually, should be W33, which is the neuron from the weight connecting the hidden to the input, and so forth. As we advance to the second layer, we increase the superscript to be 2, which indicate this is layer 2. So when we say W1 of 0 of 1, we mean this is the weight layer 1. We can have another W1 of 0 of 2, which means this comes from layer 2. This is W10 of 2. So we have two W10s, but this is for layer 1 and this is for layer 2. So if you go ahead and check what will be the algorithm in this case, so of course we present, it's going to cycle through our different data sets. So the data set is as follows. We have x of n and d of n, where we have n goes to 1 to n samples. So here we have n samples. Okay, so we can initialize weights to small random values. Okay, we can choose a learning rate that we want. So each epoch we present each data set, each data pattern. Okay, so we calculate, first step, we calculate the induced local field at layer L. So this will be Vj of L. Okay, this is the layer, is equal to summation for I goes to all the neuron in the next layer, Wji of L at dataset n times y I of L minus 1, which is the input from the previous layer. Okay, so in this case, yi of L minus 1, if L equal 1 implies first hidden layer, and yi of 0 is the input. Okay, then we compute the sigmoidal function, and we have yj of L is equal phi j of vj of n, of course, of the same layer, then if here we have two cases. If L equal 1, as we said, this is the first hidden layer, we have y, I'm going to write j of 0 of n equal x of n. Or if L equal L, which is the output layer, then we have yj of L of n is equal the output j of n. Okay, so the oj of n is actually, we'll place it on the figure, is these guys. So this is equal O1, O2, and this will be equal, this is y3, which is equal of 3 equal O3. Okay, then we compute the error Ej of n, which is equal Ej of n minus Oj of n. Of course, this is always at the output layer. When we say error, we have it at the output layer. Now, we need to update the weights. We have two cases. If we are at the output or at the hidden layer. So the local gradient at layer L for the nth data set, nth pattern, excuse me, is equal to Ej of L times phi j prime of Vj of capital L of n. This is output layer. L in our case is going to be this is layer number 2, and if it's not, if it's a hidden layer, it's going to be phi j of L of Vj of L of n times summation for all the local gradients of the next layer. Could be the output, could be another layer, times W K J L plus 1 of n, and then in this case Wj I of L of n plus 1 will be equal to Wji of L of n plus the learning rate times the local gradient times yi of L minus 1 of n. Of course, we keep on repeating this until we have a small update. Yeah, the rate where the weights are being updated is very small, or where the gradient becomes also very small, same thing. So next we will do an example. So before going into a numerical example, we're going to discuss the activation function phi and its derivative. So first we're going to consider two different examples. We have the logistic example, and we have the hyperbolic example. So in case of the logistical example, logistical function, we have the following formula. So phi j of vj of n is equal to 1 over 1 plus exponential minus a vj of n, where a is greater than 0. So we take the derivative. So the derivative of vj of n will be simply as follows: a y j of n to 1 minus y j of n. So this is one of the reasons why they choose the logistic function, because it has a very simple derivative. Now if I draw a logistical function, it's going to be as follows. Okay. Now for the case of a hyperbolic tangent, what we have is the following. We have a function that can go from negative to positive, and then we have the function of phi j of vj of n is equal to a tangent h b vj of n, where a and b are parameters that can be chosen. In this case, phi j prime of vj of n is going to be equal to b over a into a minus yj of n times a plus yj of n. So these are the two most popular activation functions along with their derivative. In the next example, we're gonna do a small example, a 2x2 network, and we're gonna use the logistical function.